All right, welcome everybody. Let's go ahead and get started here. We'll revisit these announcements. Remember that the introductory assignment's due tomorrow by 11. I think maybe a handful of you have already finished that, so that's great. Your first calculation assignment is due on Tuesday, and we're going to cover a couple of ideas, and I'll show you some equations that you need to be familiar with for that assignment. Now, of course, Monday is a holiday, so I won't be in the office on Monday, but I will try and check my email a couple of times over the weekend in case there are any questions. My little microphone's broken at the moment, so I'm going to be using this webcam for audio, so the quality of the recording, the sound quality may not, I mean, it's never great, maybe even worse. So I apologize for that. You'll have to maybe just remember what I said today, I guess. All right. So any questions on the announcements? All right, we're going to continue talking about flow resistance, which is what we started with on Tuesday, and then also talk about some different ways to classify flow and velocity distribution. But before we do that, let's take a step back to fluid mechanics. And remember that of the two, you first learned Bernoulli's equation. And what's the main difference between Bernoulli's equation and the energy equation? Because they have a lot of the same terms. Head loss. Exactly right. So the energy equation accounts for energy loss between the 2 points. So we use Bernoulli's equation in situations like that expanding pipe section, where there's a change in diameter, and so the velocity is, in this case, decreasing. And we had some limitations on how broadly we could apply Bernoulli's equation. Remember, the restriction said that Bernoulli's equation was valid for steady flow, for an incompressible, inviscid fluid along a streamline. And so those limitations about it being an inviscid fluid was all about the fact that Bernoulli's equation has no way to account for pipe friction and energy loss due to shear stress of the pipe resisting the movement of the water. So Bernoulli's equation is kind of blind to the fact that as the water flows from left to right, the pipe is pushing back against the water from the right towards the left. So we couldn't deal with that limitation. I mean, it's okay. Bernoulli's equation is okay as long as the 2 points you're applying it over are relatively close together, because 2 points that are close together won't experience much friction loss. But when the two locations are far apart, like this image on the right, Bernoulli's equation would say that there's no pressure change in a section like this, because if there's no change in velocity, Bernoulli's equation says that the two pressures should be the same. But through measurement down in the lab, you notice that even for a 1 meter section with relatively fritzy equipment, you can still measure a pressure drop across 1 meter length. And so now consider how far it is from your house to the drinking water treatment plant. There's going to be a lot of energy loss there. So we had to come up with some way to account for the energy loss. And what was the equation that you used in that lab where we were utilizing the pipe rack? You remember the name of that equation? Was it good?
Darcy, Wiesbach.
That's the one we're going to use this semester most often. Hayes and Williams. Right. There's 3 main equations that are still used today, and there are some older historical ones. But a big part of our class this semester is trying to find out how we can predict the pressure change for a pipe network, and we're going to be using different empirical equations to predict that energy loss. What's attractive about the Hayes and Williams equation, as you learned, is in theory the friction factor C should be the same regardless of pipe diameter, regardless of flow conditions, and so that makes it pretty easy to apply. The disadvantage is that it's not as accurate as some other methods. And so that's what really is the main objective of the next couple of lectures, is talking about these different empirical equations that predict pressure change due to pipe friction. So these are empirical equations, and Recall that our definition of a piezometer is something that can be used to measure the hydraulic grade line. And there are two terms that go into calculating or even graphing the hydraulic grade line. There's the pressure head term and the elevation term. And the energy grade line, remember, is the hydraulic grade line plus one other term. The energy grade line also includes the velocity head. So EGL is HGL plus V squared divided by 2G. Now here, the water level is going to rise to a certain height, and however high the water is, that is the hydraulic grade line at that point. And so we can tell from this sketch that the water is flowing from the left towards the right. If the water was stagnant and if there was no flow velocity, things would look different. The water levels would be the same on this piezometer tap on the left, the piezometer tap on the right. Right now, the water level on the right is a little bit lower. And so that's an indication that we have head loss due to pipe friction. And so if there's more energy on the left than there is on the right, that tells us the water is flowing from left to right. Now, the fact that this pipe is inclined has nothing to do with the water levels that we see. Thinking about, now, if it was static conditions, so if the water wasn't flowing through the pipe, then the water level would be at the same on the left piezometer and the right piezometer, even if we tipped the tubes back and forth. The main pipe, if we lowered one side and raised the other, that wouldn't have any effect on the water level inside the piezometer. The piezometer only has a difference in height if the water is flowing. So this is the H sub F.
Obviously the flow is left to right for that to happen, right?
That's correct.
Thank you.
So if we say the HGL is these two terms, so the change in HGL is this head loss due to pipe friction. And the most accurate way we have to model it is the Darcy-Wiesbach equation. And so the friction factor F, which we'll spend a lot of time talking about how we calculate that. We've already, in the last lecture, revisited the Moody diagram. That's a quick graphical way of estimating the F value. We also have some equations that remove the need to consult a figure. So we can put some equations into Excel, for example, or in a computer, and then, excuse me, and then you don't have to stop and each time consult the figure. So the energy loss between 2 points is a function of the friction factor, the pipe length L, the velocity term squared, divided by the diameter, and then 2G. So the Darcy-Wiesbach equation is just derived from the idea that the hydraulic grade line can be traced with these piezometers, and we know that the height difference, H sub F, if you double the length, then you double the H sub F. And if you doubled the velocity, then you'd actually have 4 times as much energy loss, because you can see that the head loss due to pipe friction is a function of velocity squared. And if you make the pipe diameter smaller, then that increases the energy loss, and that's why it's down in the denominator term of the Darcy-Wiesbach equation. So I just wanted to remind you kind of where the Darcy-Wiesbach equation comes from. But before we get to use this beautiful equation, let's revisit some of the ones that are a little bit less accurate. Now remember that if we have an enclosed pipe, the water is flowing under pressure, then the slope of the pipe can be different from the slope of the energy grade line. And so S naught is the term for pipe slope. That's the physical slope of the pipe. And S sub F is the term for the slope of the energy grade line. And so what that means is that we can have a pipe that's going uphill like this, and if the water is flowing from left to right, then the water level would rise higher on the piezometer on the left than the one on the right. And so here's our delta H sub F, This is the energy loss due to pipe friction. So the delta Z is the energy loss due to pipe friction. And so the fact that the pipe is inclined doesn't say anything about the slope of the energy grade line. So here's S naught, the slope of the pipe. It could be uphill, it can be downhill, it can be horizontal. But the slope of the energy grade line, S sub F, is independent of the pipe. Okay, your homework assignment asks you to calculate the shear velocity for a couple of problems. And I wanted to explain a little bit about what the shear velocity is. Now, in class on Tuesday, we said that the head loss due to pipe friction can be expressed in terms of shear stress. The shear stress is the resistance that the pipe is putting on the water. It's the resistance to flow on a unit area basis. And so the units of shear stress are newtons per meter squared. And so when we're doing that force balance and we wanted to find out the number of newtons of force of resistance, then we had to integrate it over the pipe area, so some length in the perimeter. But the shear stress itself can be related due to the pipe friction. And remember here that R is hydraulic radius, and so that's the area divided by the wetted perimeter. Does anybody remember what's the quick way to estimate it's to calculate the hydraulic radius for a pipe where the water is flowing full through a circular pipe? Good, that's right. D divided by 4. Because area is pi d squared divided by 4, and wetted perimeter is just the circumference around the outside of that pipe, and so it's pi d. So hydraulic radius for a pipe that's flowing full is d divided by 4. So if we combine this relationship of shear stress and pipe friction, along with the Darcy-Wiesbach equation, which is our empirical attempt to describe pipe friction head loss. This is just an empirical approximation that relies on this mystical friction factor F. So if we combine them together, we can rearrange and cancel out like terms and simplify. And this is what we end up with, is a term that on the left side has shear stress and fluid density, and on the right has the friction factor and the velocity. And what this tells us, this relationship, is that the friction factor is directly proportional to the boundary shear stress. So in other words, if the shear stress goes up, then so does the friction factor. And that makes sense that, what's causing the shear stress is it's just a natural resistance to flow. And so by increasing the velocity through the pipe, the shear stress that's resisting the fluid movement increases. And the way that we're going to account for that empirically, we have to have some equation that accounts for the fact that the shear stress is higher, because we can't go in there like with the ruler and measure the shear stress. It's not as easy as you can't directly measure it in a live environment. Instead, we want to predict in advance what the effect of that shear stress is going to be. And so this empirical equation is our way of trying to approximate the effect of the shear stress. And so what it says is that shear stress and friction factor are directly proportional. They both increase at the same rate. Now let's look at the units of shear stress divided by density. And so the units of shear stress are newtons per meter squared. And then density, of course, is kilograms per cubic meter. And so this term is just inverting, since it's in the denominator. So kilograms per cubic meter. So if we now break down the newtons into its fundamental units, a newton is a kilogram meter per second squared. And then we still have these meters squared from before, so that's what this one is. And then keeping the units of density, kilograms per cubic meter. And now if we cancel everything out that's like, we've got meters to the fourth in the numerator, meters to the second in the denominator, and so that leaves us with meters squared. The kilograms both cancel out, and then we've got seconds squared. And so someone along the way recognized, hey, meters squared and seconds squared, we could express this relationship of the shear velocity in terms of units of velocity, meters per second, if we took the square root of it. And so shear velocity squared is shear stress divided by density. And so therefore, if something is just asking you to calculate the shear velocity, what you do is you take the square root of the shear stress and the fluid's density. It's kind of an abstract idea that doesn't have a lot of everyday practical application, but if you're looking at material strengths, then the shear velocity of the fluid can be interesting to consider.
Is the asterisk just part of the symbol?
What's that?
Is the asterisk just
Yes,
part of the symbol?
it is. Yes. Right. Are there other questions about this so far? Okay, now I've put this in a little box to make it easier to find when you're working on the assignment. And so if we have now shear velocity and friction factor together, so we're substituting the shear velocity back into this relationship that tells us the Darcy-Wiesbach equation, then the fluid's flow velocity and the shear velocity of the fluid can be expressed as a function of the friction factor F. So you'll have some fun using this on the assignment. All right. Now, we do have to wait a little bit before we get into all of the empirical equations for open channel flow. But since we're on the subject of flow resistance, let's look at how things are just a little bit different for an open channel than they are for a pipe. And in engineered channels, and in fact in natural channels, oftentimes we have this trapezoidal shape because although it's easier to calculate the flow conditions in a rectangular channel, the fact is that a lot of the natural materials that are out there in the world can't support a rectangular channel like this. If you have water flowing through a rectangular channel, then the materials are going to just kind of slope into the channel itself, and collapse in. And so there you could have a rockline channel, or if you had reinforced concrete, you could achieve a rectangular channel. But this trapezoidal shape is more common. So the geometry of an open trapezoidal channel is pretty important in this course. And so we call the bottom width of the channel lowercase b. The top width, depending on which resource you're using, like the FE manual and textbooks, all kind of flip back and forth whether they call this T for top width or uppercase B. So I'll just let you know that those two can be considered as interchangeable. There's one of the parameters is the bottom width, one of the parameters is the top width. And then there's some factor that relates the slope, how steep the side slope is. And so there's a vertical component, a horizontal component, and if we say that this is 1 unit of vertical, and then we'd assign the side slopes to be like a t factor. So we could say t equals 2, and what that means is for every 1 meter of rise in the side slope, there's 2 horizontal meters of length. Okay, so this is a pretty important geometric parameter, and remember that shear stress can be approximated as the unit weight of the fluid, the hydraulic radius, which depends on the geometry, and then the slope of the energy grade line, S sub f. And hydraulic radius is the area divided by the wetted perimeter. And so the same kind of relationships exist in open channels and in enclosed pipes that relate flow resistance and flow rate. But one of the differences here between what we were just talking about for pipes is that the slope of the channel and the slope of the energy grade line are equal if the flow conditions are steady and uniform. And so remember I said that the pipe slope and the energy grade line slope are independent for enclosed flow, and that's because it's pressurized. That's because the water's full to the very top of a pipe, and so the pipe can go up and down, and it doesn't affect the energy grade line. But when there's air in contact with the channel, then the slope of the energy grade line is parallel to the slope of the channel. So the two are equal if conditions are steady and uniform. Now, just to get some early exposure to trapezoidal geometry, what's the hydraulic radius for a trapezoidal channel in terms of the bottom width and the depth of the channel? And so I want to know what is R. And so I'm going to pause for a moment and give you time to calculate. How can you express what is the hydraulic radius of a channel in terms of B, Y, and then I guess also this function T. So let me change this question in terms of B, Y, and T, which is the side slope. All right, so in other words, what we want to have is hydraulic radius is what? How would you calculate the hydraulic radius for some B, Y, and T? And so what you have to do is just kind of look at this geometry of a trapezoid and figure out what is the area in terms of B, Y, and T, and then what's the wetted perimeter. Now the top of this is in contact with the air, so it doesn't count in wetted perimeter, the top of the channel. So this uppercase B isn't a part of wetted perimeter. Wetted perimeter is only where the water is actually touching the material that's stationary, the solid material that's stationary. So we'd include this side angle length, the bottom width, and then the other side angle length. All right, I'm going to give you a minute to think through this. We want to know the area and wetted perimeter so we can calculate the hydraulic radius. Okay, so I was walking around and I think people were either getting it or we're on the right track. So let's look at this, this trapezoidal geometry here. For a certain depth y, then there's going to be some extra width to the right on the top that is t times y. And the way to think of that maybe is with actual numbers. What if it was a 1 to 2 side slope? So if it was 1 to 2, that would mean however tall the water is, there would be twice as much width over on the right side, and then also that same length over on the left side. So that's whatever the depth is times the t factor tells you the additional distance on the right across the top. So then with that, the area is b times y, which is the area of this rectangular section. So the width times the height. So that gives us the rectangle. And now we need to find these two triangles. If we combine the two triangles together, it's another rectangle with an area of ty times y. So that's where we get the cross-sectional area formula. And then for the wetted perimeter, what we have to do is we have to find these side lengths. And there's two of them. There's one on the left, one on the right. And so if this is ty is the top part of that triangle and y is the height of it, then we have to square each side and find the square root. So the square root of y squared plus ty, which is squared, then there are two of them. So it is the wetted perimeter is the bottom width and then 2 times these side lengths. So that is given on page 301 if you want to make a note or revisit.
I don't know if you already went over this. I'm having a hard time seeing where you got the ty to be the length.
On the top?
Yeah.
It's because by definition, t is however much width there is in this side slope angle for each unit of height. And so I think it's most obvious if we try it with real numbers. So let's say it is 1 to 3 side, and then what if the depth of the water is 5? So if the depth of the water is 5 is to 1, as this top width will be to 3. So this top width would have to be 15 if the depth was 5, because what we've defined is this angle is at such an angle that for every unit of vertical, there's 3 units of horizontal. So then if we go back to the abstract again, if we say that we're just going to call this t, and then the depth is y, then that means however deep it is, there's T times that depth across the top. Yeah.
I always have problems with that, and Mike pointed out that the bottom side was longer, and the way it was drawn, it was just throwing us off. But if you look at the actual picture, the T's actually longer on it, if that helps you. So you know the whatever's longer.
So you're saying that it just kind of makes more sense to you if this is longer than 1?
Well, the drawing, because there it looks equal, like,
Yeah.
it's a 45, 45.
Yeah, this is definitely not to scale. Anytime I pick up a marker, you can guarantee it's not to scale. And probably not legible, but okay, good point. Are there other questions about this one? Yeah.
So can we think of the triangle as kind of like a slope ratio?
Mm-hmm. Yep. It is. Slope ratio. That's a good way to put it. Okay, so the Darcy-Wiesbach is kind of the gold standard that we use when we really care. But back before it was convenient to do the challenging calculations required to get an F value, and before they'd characterized a lot of pipes to find out the information that goes in to the Darcy-Wiesbach equation, one of the first empirical flow resistance equations was the Chesi equation. And the Chesi equation says that there's a relationship between the hydraulic parameters that go into the hydraulic radius and the slope of the energy grade line with what the flow velocity is going to be in a channel or in an enclosed pipe as well. The Chesi equation can be used in either. And so there were these Chesi roughness coefficients that were developed, and the error that's built in to using the Chesi equation is pretty large, because in the same way that the Darcy-Wiesbach equation does account for changes in flow conditions, you remember that the Hazen-Williams equation didn't last semester. You calculated some C value that was supposed to be constant regardless of what the flow rate was, regardless of the diameter, and so on. So here the Chesi equation is in a lot of ways similar to the Hazen-Williams equation, where a very rough pipe would have a low Chesi equation because you'd want the velocity to be low if it's a pipe material that's rough. And if it's a very smooth material, then the C value would be much higher. The Manning equation later improved on the Chesi equation, and that is one equation that is still in use for open channel flow. Although the Manning equation isn't usually used for pressurized pipe flow. So just a little bit of a history lesson that there are simple and older equations to estimate empirical friction effects, and the Chesi is one of them. Now, in your book on page 201, there's an equation that tells you how to relate the friction factor and the Chesi equation. And so, in very rare cases, you may find infrastructure still in place that was designed back when the Chesi equation was utilized. You think about some of the older municipalities here in the eastern half of the United States. There are pipe networks that have been in place for more than 100 years, and so you may find yourself looking at an old design drawing or some old design calculations that use the Chesi equation. And so if you needed to convert between the Chesi equation and the Darcy-Wiesbach friction factor, this is the equation that you could use. And they're both based on a relationship of shear stress tied into the slope of the energy grade line. So that's where this equation is, page 201 of your book. Okay, you remember that we've talked about velocity distributions before, and that if the flow is moving slowly through a pipe, conditions are laminar. If the Reynolds number is less than 2,000, then that means that the laminar layers are slipping over each other without introducing a lot of turbulence. And this parabolic velocity distribution is a really smooth and regular way of predicting what's the velocity as a function of the radius from the outside of the pipe. And so what we're looking at is this would be the bottom of the pipe, where there's zero velocity because the water that's immediately in contact with the pipe remember, is experiencing the no-slip condition, where it can't move at some positive velocity over a surface that's causing resistance. Instead, the water velocity is 0 at the pipe, and then the further away you get from the edge of the pipe, the velocity is increasing. And so this is the middle of the pipe, where there's the least amount of resistance, and if conditions are laminar, there would be a parabolic distribution of this curve. And then, of course, as you approach the top of the pipe, the other side, then the velocity is decreasing again until it reaches 0 at that top edge of the pipe. Turbulent flow conditions, instead of having this bullet-shaped velocity distribution, it's a flatter edge. And that logarithmic shape means that now there's a lot of random variation. This would be kind of the average velocity over time. At any given time, one section may have a low velocity, some it may be higher, but over the average, it would be a logarithmic shape. There's a phrase that we call fully turbulent flow. And if we go back to the Moody diagram that we looked at in class last time, it differentiated between these two flow regions. The rough turbulent is also another way of saying fully turbulent flow, and transitional flow. In the rough turbulent zone, what it means is the friction factor is not changing as the Reynolds number goes up. Past some certain threshold, you can continue to increase the flow velocity, and the friction factor no longer depends on an increasing velocity. The friction factor only depends on the relative roughness once you get into the rough turbulent zone. But on the other side of this rough turbulent zone, here in transition, or if the flow is not fully turbulent, then the friction depends both on the relative roughness and on the Reynolds number. So this is the same when we differentiate in the Moody diagram these two different zones. That's what we're continuing to talk about today here with the idea of fully turbulent flow. And this sketch shows two different flow conditions. A relatively slow-moving flow where conditions are laminar, and then turbulent flow. And this sketch is at the edge of the pipe where there's a lot of resistance. Then the conditions, remember, the velocity is low at the edge of the pipe. Going back to this sketch is a sketch of velocity. So here's the edge of the pipe at the bottom and the top. So low velocity means that there's going to be a lot of shear stress. The high shear stress in the fluid, because that's right at the boundary where the pipe is pressing against the fluid to resist its movement. This boundary, the thickness of the boundary layer can be thought of as the region where where there's very little flow. The conditions are laminar throughout this boundary layer. But then the further away you get from the edge of the pipe, the shear stress is decreasing. And so there's two different conditions that are kind of summarized here. A condition where this is what the shear stress profile would look like for turbulent flow. Here's the shear stress distribution for laminar flow. It's how far into the pipe the shear stress is affecting conditions. And so if it's relatively low velocity through a pipe, then the shear stress doesn't extend out into the entire cross-section of the pipe. So this top represents the center of the pipe, where you're the furthest away from the wall of the pipe, and so the shear stress is the lowest. The thickness of this boundary layer is important for a variety of reasons, and so what we're going to look at is some equations that calculate how thick is that boundary layer. The boundary layer depends on the degree of turbulence and also the material of the pipe, like what it's made of, is going to have an effect on how thick that boundary layer is. You can think of this boundary layer as kind of like a cushion. It's a fluid cushion at the edge of the pipe where conditions are laminar. And then when you get out of that boundary layer is where the flow conditions are with the Reynolds number above 4,000, so the turbulent. So this is kind of just another way of looking at the velocity distribution. The fast flow velocity is going to compress the boundary layer, where a slow velocity may have the effect of increasing the boundary layer depth. This is a table that can be found in your text that's describing different materials and their equivalent roughness. Sometimes that's also called the equivalent sand roughness, because what it's doing is it's comparing each of these different pipe materials into how much flow resistance there would be from a sand grain of a certain diameter. So you can see that galvanized iron, the roughness and the effect of that roughness on moving water for new galvanized iron is the same as if you had some pipe that was lined with sand grains that had an average diameter of 0.15 millimeters. Or if you had wrought iron, a steel wrought iron pipe, it's more smooth, and so you'd have to have a finer grain material to have the equivalent amount of resistance to flow. There are some pipe materials that have a very high equivalent roughness, particularly concrete, that becomes rough over time. If there's a chemical attack of the cement, then all that's left exposed in some concrete would be the sand grains, and then also like the aggregate. But sometimes in sewer pipes that can be a problem, because in sewers there's a gas that's called hydrogen sulfide that's formed. It dissolves in the water and it forms sulfuric acid that can erode a concrete sewer pipe. And so sometimes if you're designing the flow conditions, assuming that you've got a really smooth, newly manufactured concrete, over time the material properties can change, and then if the pipe becomes more rough because the cement is being dissolved out, then that would mean it's less efficient for carrying flow. So it's kind of a compounding problem. I think it's kind of interesting to see that they've bothered to figure out what's the equivalent roughness of wood pipes, and I don't know if there are any places still that have wood pipes in operation, but that's how they used to have water flowing through pipes, in the same way that they have like barrels for whiskey or for taking water from place to place. They'd have metal wiring going around the outside of pipes, and so that would be very labor intensive, and I assume extremely prone to leaking. On your assignment there is a problem where you have to calculate how thick is the boundary layer for some certain flow conditions. And Morris and Wiggert together came up with an empirical equation that estimated how thick the boundary layer is based on the shear velocity. And you remember we just looked at the shear velocity equation earlier. It's the ratio of the shear stress that the fluid is experiencing divided by the density of the fluid. And so here this little sketch is showing that there can be different effects if the laminar thickness, if the thickness of the boundary layer fully encloses the roughness heights, then there can be one flow condition, and we'd call that hydraulically smooth. So the limit is that if the boundary layer thickness is greater than 1.7 times the roughness, then we say that the laminar sublayer dominates the roughness elements, and so therefore it's hydraulically smooth. So these little projections, you can think of them as, remember, it's almost like we're gluing sand particles to the inside of a pipe. These little particles are below that cushion. The laminar layer is where conditions, it's how thick conditions are laminar, with the Reynolds number below 2,000. But sometimes the laminar layer is very thin, and the roughness elements go beyond the thickness of that laminar sublayer, and so that's hydraulically rough. Now you'll notice that there's a pretty big in-between ground. You know, hydraulically rough is if the laminar sublayer is less than 0.08 times the equivalent roughness. And hydraulically smooth, it has to be greater than 1.7. And so in between is a transition zone. Similar to how Reynolds number has this transition zone between 2,000 and 4,000. So hydraulically smooth and hydraulically rough, these will come back again when we're actually doing some hydraulic calculations. We want to make assumptions, like we were looking for ways to simplify our calculations. We'll sometimes start off with a guess on whether conditions are hydraulically rough or hydraulically smooth. And so it'll be a way for us to, at the beginning, make an assumption that simplifies all of our calculations, and then we check to see if the assumption is true. So this is just a little bit of the theory that we'll use later on to make it easier to finish calculations. Okay, well, let's finish up today with one more calculation, one more example here. Let's say that we have an elevated water tank that's provided water to a building, and you can see from the problem statement that we're delivering 12,000 liters per minute, and at the ground floor of this office building, we want to make sure that the pressure is 350 kilopascals. And we know the pipe length is 250 meters long, and the diameter is 250 meters. And the friction loss is 16.4 meters. So if you know the friction loss, then that in effect is going to tell you what elevation you need to have inside the tank to be able to deliver the water. So in other words, H sub F, in this example, we're going to assume that all of the head losses are due to pipe friction. So H sub L is H sub F. We'll neglect the minor losses in this case. And the problem statement tells us that they are altogether 16.4 meters. Okay, so in part A, I'd like you to use the energy equation and solve for Z1. Find out how tall does the water have to be inside of that elevated tank to make it all work, so that we have enough pressure, so that we come over the friction losses. And let's assume that you are accounting for the velocity head at 2, but at 1, since that's a tank, a reservoir of water, we'll assume that the velocity inside of the tank is 0. So you'll be able to cancel out the velocity head at 1. And then once you have that solved, calculate the friction factor that accounts for how much friction loss we're seeing. So in this case, we'll be solving for F with all the other given parameters. And then I'd like you to get a chance to practice out the thickness of the boundary layer inside the pipe with the Morris and Wiggert criteria. And I'll try and copy that over from the previous one. Here's the Morris and Wiggert. I'll paste this into the example. All right, so I'm going to stop talking. You can work with your classmates, collaborate on this one, and we'll revisit. Make sure we're all getting the same numbers. By the way, I added all of the equations in one place so that you don't necessarily have to flip through the notes for part C. Okay, in part A, we're calculating how high the water has to be in the tank. Part B, we want to ask what's the friction factor that's causing this friction loss. In part C, we're just getting some practice with the thickness of the boundary layer. Okay, so here's the solution to calculate the elevation of the water in that reservoir on the left. We have to do some of the preliminary stuff at the beginning, like calculate what's the flow rate, not in terms of liters per minute, but what is in meters cubed per second, because we're going to need to calculate the velocity of the water that's flowing through the pipe, because although we're going to cancel out the velocity head at 1, at 2 we're taking that to be the pipe just before it gets to the building. And so it still has velocity head when the water's in the pipe just before it gets to the building. Okay, so you can see all the substitutions that I've made into the energy equation. P1 is 0 since we're at the free surface of the water inside of the tank. Z1 is what we're solving for. The velocity of the water inside the tank is 0. P2 is the pressure that we're trying to achieve at the bottom floor of that building. Z2 is the given elevation from the sketch. You can see that the elevation above our datum is 20 meters for the building. And then we've got the velocity head and the given head loss. And so when you rearrange everything and solve for Z1, it should be 72.9 meters. And you may get slightly different values depending on how many digits you take the velocity head to on the right. Any questions about Part A, how we calculated the required height of that tank? All right, so now when you're given the Darcy-Wiesbach equation and all of these terms are already defined in the problem, we have a known head loss, a known pipe length, the flow velocity can be calculated, the diameter. We can just rearrange that to solve for the friction factor F, and it'll be 0.0194. And now this last part is maybe the tricky stuff here, because before I put the equation on the screen, you had to remember what is the slope of the energy grade line, S sub F, because you're going to have to put that into the equation that relates shear stress and slope of the energy grade line. So the slope of the energy grade line is the head loss relative to the pipe length. And so here we've got the slope of the energy grade line as a fraction, and if we substitute that into the shear stress equation, we can find that the shear stress is about 40.2 newtons per meter squared. Did everybody get that for the shear stress? Yep. Okay. Now we want the shear velocity. Now that we have the shear stress, we can express the shear stress in terms of meters per second by taking the shear stress divided by the density and the square root. So the shear velocity is 0.2 meters per second. And now we put it into this Morrison-Wigert equation to find the thickness of the boundary layer. So it's 11.6 times the kinematic viscosity of water, and then divide by the shear velocity. So it turns out the thickness of the boundary layer under these flow conditions, it's going to be 0.058 millimeters. And so then what we could do if we knew more about the pipe is we could look and see what's the equivalent roughness. And then we could see, are those roughness elements fully submerged by the laminar layer, and therefore we have rough turbulent flow, or do we have smooth flow, or is it in the transition zone? But I think that this example should be pretty good practice for the assignment that's due on Tuesday. Are there any questions related to the example before we wrap up? Yeah.
I used the ratio, the velocity over the velocity over shear velocity equals the square root of 8 over your friction factor in order to find that shear velocity to V star, and was able to come out with the same.
So, not this one. One of the earlier equations that we had.
I believe it's
Which one?
Velocity over shear velocity equals square root of 8 over the friction factor. Right?
Okay.
It was in the box.
There, this one.
Yeah.
Yeah. This works if you know the F value. And in this example you did.
Okay.
Yeah, you knew the F value. So
you
you
could use that and then
sure.
you know the F value.
Yep.
Okay.
The F value was a proxy for everything else.
Right.
All right. Before we wrap up, let's just glance one last time at these announcements. The assignment 0 is due tomorrow by 11. And homework 1, please upload it to MU Online before class on Tuesday. Hope you have a good long weekend. I'll see you next week.